and then go to the University as an assistant professor, and move to National Government University, and then become professor, and then become the department head, and then he established the center of the mathematical modeling and scientific computing, and also established the graduate program of this. He got full times of distinguished research award, the National Science Council, and also the distinguished research award of our society, recognized. And he has a great contribution in the Numerics boundary method and its application. And he also has an important contribution in the fluid and structural intention. So let's welcome Professor Mizla.
Thank you for a nice introduction. It's my great pleasure to be here, and also a great honor to be invited as our annual meeting of Taiwanese Mathematical Society, okay, to give a talk. Okay, so today I'm going to talk about my recent a couple years research along the direction of fluids with interface. Okay, so today I'm going more focus on the models, numerics, and the applications. Okay, so basically, this what I'm interested in is called interfacial flow problems. Okay, mainly that, for example, a fluid droplet, okay, immersed in another fluid. Okay, this is two-phase flow. Okay, it happens to our daily life experience. Okay, also from material science, you suppose you have some material, then immersed in another matrix material. So there's an interface between those two phases. Okay, so basically, these are issues for the two-phase flows. So the drop surface, this interface, will deform due to the surrounding fluid. Okay, so that's the main behavior for the two-phase flow. So the question is how to represent the interface. So the interface is going to move, okay? And how we are going to represent that and to track that. So how to track and capture the interface evolution, right? Like I say, for example, the droplet, okay, in a oil droplet in the water, okay, because the oil is not immiscible with the water, so the shape of the droplet will deform, okay, due to the surrounding fluid water. So questions how to track this kind of interface evolution. And another issue about this two-phase flow will be how to impose the stress-force balance condition at the interface. Okay, those stress-force may depend on, for example, the mean curvature. For example, the surface tension force will depend on mean curvature, or also the surface Laplace of the interface. Right. So I will get to that, okay, later on. So basically, when you're dealing with the fluid with the interface or the binary fluid structure, you are going to handle the interface. So that's the main issue I'm going to talk about. So other than that, if we want to do some extra, more complicated problem, you have to deal with another issues. For example, suppose there's some surface material quantity, let's say a surfactant, okay? The surfactant exists along the interface, okay? I will give you some definition. What is the surfactant? No? Then you have to handle that. You need to solve PD on moving surface, okay? Remember, your surface is moving, your interface is moving. Then you have a PD, you have some quantity. Of course, it's also time dependent along the interface, right? So you have to solve PD on moving in surface. Then that's extra one issues. Another issue, what if there is some constraint such that like insensibility on the interface? Okay, for example, I will take an example, a vesicle. Okay, the vesicle is a simple model to mimic red blood cells. The vesicle, the total area of the vesicle doesn't change. Okay, so the vesicle can deform, but the whole area won't change. So that's what I say is a global constraint, but it should be a local constraint. That means there will be some insensibility on the interface. We need to impose some PD on the moving surface. Okay, so this is all the interfacial problem that I'm going to talk about. All right, so major numerical method just for two-phase flow, handling two-phase flow, include the immerse boundary method, which is proposed by Peskin in 1972 to study the block flow in the heart. Okay, and later on, some others. And the continuous surface force method, which is very similar to our immerse boundary method, also this from tracking method. And there's the other method which is based on boundary integral method. This mainly on the Stokes flow. Okay, so the Portkidius wrote a book, very nice book. Okay, about this boundary integral method. Then other method is volume of fluid, and the from tracking method. Okay, our method immerse boundary is very similar to this from tracking. Basically, we just track the interface. Okay, you have a different method to track interface. For example, level set method is a good method to track the interface. But when you deal with some other issues, especially like the two extra issues that I was talking about, that you need to solve PD on the surface. Okay, but level set method, you don't know where it's the surface exactly. Okay, because it's defined by zero level set function. Then also phase field method. Phase field is diffuse interface method. All right. So this is a method to handling the two-phase flow. Okay, so a few years ago, when I tried to study, use immerse boundary method to study the fluid mechanics problem, then one problem comes to my mind is we try to solve the interfacial flow with the surfactant. Okay, this is a surfactant. This is let's see, some kind of a stain. This is your clothes. Okay, this is without surfactant. Okay, right now you can think about the surfactant just a detergent, which you use in the daily life laundry. Okay, detergent. You put detergent, then this put detergent. This is water, and this is some kind of oil, some kind of stain. Then you put detergent. A detergent, which is a surfactant, likes to stay in the interface here. Okay, this interface to change the surface tension here, then make this hydrophobic drop even more hydrophobic. Okay, so in other words, it will detach from this solid surface. All right, so then become here. This one, this is with surfactant. So this is the effect of a detergent. I just make a copy from some books. Okay, so with surfactant is this. So think about you have some kind of oil stain attached to your clothes. When you do laundry, you put the detergent. There's a function on that. Okay, so you have to remember when you do laundry, you need to put some detergent. So in order to make this dirty step become this one, then the water can wash away this oil strap. Okay, so basically in this issue, there's some two issues. One is called a moving counter line. At this point, this is solid. This is solid. At this junction, triple junction, we call it a moving counter line. Okay, counter line, and also the surfactant. So there's basically two issues. Okay, on the counter line, there's a so-called equilibrium contact angle. Depends on this surface tension here. All right, this is surface tension between solid and gas, and surface tension between suppose the liquid is here. This is the contact angle, and this is surface tension gamma. Okay, when the droplet is steady, okay, which is the equilibrium contact angle. These three surface tension related by this equilibrium contact angle, this one. Okay, basically is the force here will be balanced, right? That's the idea of equilibrium contact angle. Okay, so when I try to study this problem, okay, this when we develop this method, you know, I just want to make sure whether our method is right, is valid, okay, and so we start to simulate a problem, okay. So first the problem will be at least phenomenologically correct, okay? So that's our first intention. Then later on we will move to whether our simulation is quantitatively correct, right? So this is, in order to simulate that problem, so we set up a problem as follows. So this is fluid, different fluid, and we'll put the fluid in the box, okay, model. And then this is the contact line, okay, solid, we call sigma S1, this is solid to and fluid. You have this is fixed, okay, and this sigma is not fixed, okay, because we have some surfactant around this interface to change the surface tension, okay. All right, so basically, so this is the model, which is we studied the interfacial flow with surfactant, all right. Basically, you have a Navier-Stokes equation. Okay, we write it down here as a dimensionless form. Re is the Reynolds number, Ca is Capillary number. Okay, and you have a divergence U equal to 0. Then here along this one, okay, like I said before, there will be a stress balance jump condition across this fluid. Okay, then we can write this stress balance condition as a singular force just exists along the interface. So that's F appears here, and then so this F is a singular force term. Okay, just occur along the interface. Right. So here we just neglect the gravity. Right. And the interface is moving according to the local fluid velocity, which is partial x partial t equal to u, and u is interpolated at the interface position. Okay, and then the force it can be written down by partial as sigma tau. Okay, sigma is surface tension, tau is unit tangent. So supposedly sigma is constant, then it becomes sigma and partial tau partial s. Partial tau partial s gives you the curvature times normal normal vector. So that's the regular surface tension force, right? And tau is written this way. Then you need to solve this partial gamma, this surfactant equation. Okay, this gamma is surfactant concentration. So along that interface, you need to solve this equation. And this gamma, when you have a surfactant, you reduce the surface tension. The loss relation is written by this so-called Ramirez equation of state, which is sigma gamma equal to sigma c, which is when gamma equal to 0, this clean interface, the surface tension of clean interface, right? So here, U is just a velocity P pressure, okay? And everything is radial. So, and for that problem, we need to handle the so-called moving contact line problem. So in 2010, along with Hua-Xiong Huang in York University and my PhD student who is now in Canada as a postdoc, and we solve using so-called slip boundary condition, and at the contact line we use unbalanced Young's force at the contact line, okay, to simulate problem. Okay, rather than use no-slip boundary condition, we have to use a slip boundary condition at the solid wall. Okay, and beta is the slip length. This slip length is very small, just a two mesh, two spatial mesh, and this unbalanced Young condition, and this slip condition coupled with the contact line condition turns out it's very similar to the effective boundary condition at the contact line proposed by Weinan Yi and his student Ren Wei-Qin in 2006. At the contact line, they impose this so-called effective boundary condition. You see how similar are those two equation, but this is the force, and here is the contact line velocity, okay? And we don't impose contact line velocity. Rather than to impose contact line velocity, we impose contact line forces. All right, so basically this is the hydrophobic case. You can see that our simulation, this is the original initial data, okay, for the drop, and then you can see that for high, without surfactant is the dashed line, with surfactant is this solid line. So you can see that with surfactant, this droplet will be attached along this solid surface. Okay, so but this is just a cartoon problem. Okay, we know the exactly behavior of the problem. We like to check whether our model can simulate some problems. So we move on to another problem. Okay, this is I'll skip that one. Okay, so this is the one that I'm right now we are working on with experimentalists. Okay, these experiments by group of Pan Guolong in National Taiwan University. I'm going to explain that. Okay, so basically this is this experiment data. This is two droplets. Okay, this is water. Okay, the water droplet collision. Okay, you can think about the water droplet, just two water droplets collide each other. Then they will, this is called collisions. Okay, that means they will merge together. All right. So as long as the speed, okay, the impact speed is small, you can expect they are going to merge together, collisions. All right. And this is still some you can imagine, right? So but however, if this is the droplet, okay, collision in air, okay. So two droplets will do experiment on that. So at this region is collisions, at that region is bouncing, okay, and then in this region is separation. Now let me show you the picture of what the bouncing and collisions and separation. This is separation. So they sort of come together, okay, merge. It seems to merge. Okay, then they separate. All right, in that kind of region. However, for the water, if you add some surfactant, just a little bit surfactant, then the behavior totally different. Okay, so here is a collisions region, but you add just a little bit surfactant, you put some detergent on the water, then you make it collide each other, then you will see something different. Okay, so now the bouncing region is enlarged. All right, means that in this region there's a bouncing. Okay, bouncing means that okay. Let me show you the picture. This is bouncing. Okay. Then you add more surfactant. Okay, then the bouncing region enlarge a significant amount. Okay, so this is a bouncing region. So that means so that means the surfactant have some physical mechanism to affect this kind of behavior, right? So then you put more to let the surfactant pass the CMC limit, which is what the CMC limit means. The function of surfactant is to reduce the surface tension. Okay, so if we pass the CMC limit, the surface tension is not going. When you put more surfactant, it's never ever to change the surface tension again. So it's sectorized. Okay, so basically, it's this is what we observe in the experiments. Okay, so we like to see why is that? Okay, we know this kind of phenomena for the two droplets in liquid. Okay, but not in the air, and I also want to mention that the Professor von Senka wrote a paper about how can I say, bond stability, okay, with surfactant, okay. So that her theoretical result says that the surfactant favors the creation of interface, okay. So creation of interface also stabilizes the phase region. Look at that, okay. This is without surfactant. This is with surfactant. You can see that this with surfactant, it favors interface creation, okay, and also stabilizes this kind of phase regions, okay. So the question, because experimentalists they saw it, that's what they observe. But we like to know what kind of mechanism, what kind of physical mechanism behind that in order to understand what we observe. Okay, so there's a different issue, different possible mechanism. Or we know the first capillary force. That means you reduce the surface tension. Okay, there's of course reduce surface tension. So this force is going to reduce, right, surface tension. And also because you have a surfactant along the interface, if the concentration of a surfactant along the interface are different, so there will be a gradient of the surface tension force, which is we call a Marangoni force. And then because the impact, okay, is very close. The two droplets very close to each other. Okay, so close to that, the intermolecule force might have some effect. Okay, so intermolecule force, for example, bendable attractive forces, and also the electrically double layer repulsive forces. Okay, this could have some effect. So we would like to know which one is dominant. Okay, basically. Okay, and once we understand this kind of behavior, then we can manipulate the droplet. Okay, then it could be a lot of the application in industry. Okay, so basically we have an experiment, right? So we like to see what mechanism. So the one way we do is we try to use the numerical investigation. We try to use the numerical study to do that based on the method that we previously developed. Okay, so that's basically using acid symmetric setting and also soluble surfactant. Okay, in previous slide, what you see is insoluble surfactant, meaning that the surfactant just along the interface, not the bulk fluid. But for the soluble surfactant case, the surfactant is just along in the bulk fluid. Right? So basically, okay, MC right time to play movie. MC is me, so I call myself to play movie here for you. Okay. Okay, so this is a drop collision. Okay, basically, it seems like the two droplets touch and they are collapse. And in fact, this is a global view, but this is very to show. Okay, so okay, all right. Okay, they didn't touch each other, and they bounce back. Okay. This is because the sizes are different. Okay, the scale are different. So basically, what you see here is okay. So what you see here is that this is a thin film here. So in order to droplets will condense, so the air should drain out of this region. Okay, so that's then the two droplets will be emerge okay, will be merged together. So that's the idea. So basically, so we start to do some simulation. We like to make sure which one is the dominant effect. Okay. So we do the simulation. All the data are from experiments. Okay. And also the surface tension, the function of surface tension and the surfactant concentration. Here we don't use any linear equation of state, that's the theoretical, because our surfactant concentration is very little. For example, when 0.1% of a surfactant, so the linear equation is not valid at that region. So we have to use experiment to fit the data, okay? To fit the data to get the relation function of a surface tension. So basically, what you see here is the surface tension 1 and 0.43, and this is the. So basically, what you see here, this law means that the capillary force doesn't affect, okay, the major behavior. And however, okay, if we add a little bit surface surfactant, for example, 0.1%. Okay, look at that. Without surfactant, this is DC, this is DR. Without surfactant, DR goes to 0. However, the DR will behave like this one. That means this is bouncing, and this is clearance. Okay, so what we see here is we saw that we can tell that the physical region of bouncing is due to the Marangoni stress. Marangoni stress because of the surface tension, because of the surfactant concentration are different. Okay, that causes the Marangoni stress. Okay, we also check whether the intermolecule forces affect this physical behavior. So we try to use unrealistic. Okay. We know the exact value of the constant, okay, but here we just use unrealistic one, and this, for example, this B star, I think is Debye constant. The Debye constant should be this kind of range, okay, should be this kind of range, but we need to. In order to have the bouncing behavior, so our Debye constant should increase to 100 in order to have the bouncing. All right. So that means the EDL effect is not the dominant effect for our behavior here. And also, on this we use unrealistic we go constant. The A star should be. The realistic A star should be 10 to the negative 11, this kind of magnitude. But we need to use something like a 10 to the minus 6, then we will have some kind of effect on this bouncing region. Okay, so basically from this kind of simulation, we know that the main mechanism behind this behavior is because of the Marangoni stress. Okay, so basically for the soluble surfactant with flows, we have a different, for the past years, different researchers are doing. Most of them, insoluble surfactant case will be easier than this soluble surfactant. I will get to that point. Why is that? Okay, and then you have a different conservative and a phase field method. Okay, this is all with flow. I know Professor Fonseca, basically from the paper that he wrote in Archive in 2007 to study the form stability with surfactant. Okay, then later on, in that case, I tried to use to solve the insoluble surfactant problem, use the phase field method. Okay, because the phase field is easier to handle the interface, right? But when we try insoluble surfactant, so that means the surfactant should stay on the interface. But when you apply shear flow, the surfactant will go away from the interface. So we are not going to keep the surfactant along the interface, right? So that's why, but at that time we saw, that's the first place I know that Professor Fonseca's work. And then this year, then Deng Junhao and Chen Yiliang and myself, we sort of modified the model proposed by Professor Fonseca, and then we added some term, and then we did check that numerically, check that by adding surfactant, the interface is favors to creation the interface, okay, and also the stabilize the phase region, which is exactly what we see in the experiment. Yes. Okay, so this is the rest is more the technique part. So basically, this is the droplet sigma 0, and this is the interface. So the sigma 1 is another domain, which is bulk fluid domain. Okay, so basically your surface concentration is defined along the interface, and because the surfactant is soluble in the bulk fluid, so you have another bulk surfactant concentration here in omega 1 region, and then the interface is moving according to the given incompressible velocity field. Right? So we use this kind of model. I want to write out the soluble surfactant equation, okay, just without fluid. Right now the velocity is given. Okay, later on we can put the Navier-Stokes into this one. So basically it's a couple of surface bulk convection diffusion equation. This is our surface concentration equation. So you can see basically this partial gamma partial D is material derivative, and this surface divergence U gamma is because your surface is going to stretch. Okay, so basically this is this term, and you have diffusion, then you have absorption and distortion term. Okay, so and that's for this equation is defined on sigma, which is interface, and then. And the omega 1, which is exterior domain, okay? Then we have this bulk concentration equation, which is the convection diffusion equation for the C equation. And then, because the surfactant, this is the flux, you know, the flux, because the bulk surfactant and surface surfactant, the gamma and C, this is the surface concentration, meaning that the unit is the mole per meter, for example, okay? And this is the volume concentration, meaning that the unit is the mole per the volume, okay, MQ, okay? So basically there's a flux between this, the source, this source term will be the flux of this term, okay? And the outside will be just a zero Neumann boundary condition. In here, CS is the C, all right? CS is, I wrote it this way because later on I need to use a different notation. And so this gradient S is just surface gradient, okay? Which is the gradient minus the normal component, right? And this is surface Laplacian. So basically, this is the equation on the interface, and this is equation on the bulk equation. And the PE and PES is a different Peckley number. Okay, one is in bulk, and the other is in the surface. Right? And sorry. Okay, so basically, there's a total mass conservation properties here. The rate of change of surfactant mass along the interface will be the time derivative. You take a time derivative as totals. This is total surfactant along the interface. Okay, you just put the time derivative here, and then you get this term, and then you use the previous equation, then you get this one. Okay, then because the interface is closed, this is drop off, and then you have this term left. Okay, so this is the source of a surfactant in the interface comes from, of course, absorption, distortion from above. Okay, and remember, this partial gamma, partial T is the material derivative. Okay, so the rate of change of mass in the bulk fluid will be this way. Okay, and then again, so this is the material derivative. Then you use the previous equation, which is for the bulk equation. Then you use the divergence theorem, then you get this. Okay, it's a minus sign. So you add up these two terms together, it's give you the total surfactant mass is conserved. Right? So same formulation in 3D. Okay, what I show you is in 2D setup, but in fact the 3D equations are the same. All right? Okay, so let me why this problem is kind of difficult to solve. Why is that? Okay, so the question is how to solve this couple. Remember, the interface is moving as time goes. Okay, so you solve the couple surface. How to solve the couple surface bulk convection diffusion equation efficiently? Because sigma is moving, so you have to solve the PD on moving surface. Okay, for the 3D surface, for 2D, of course, it's curve, right? And then because the bulk fluid is outside of the interface, so the domain is changing. So you need to solve a PD on irregular domain, which is a moving irregular domain. Okay, so question is how to solve that. Then can we preserve the total surfactant mass? Like I say, mathematically, the surfactant, total surfactant should be conserved, right? So can we develop a numerical scheme based on this kind of conservation? Right. Then how to avoid the insolubility of surfactant, because there's no surfactant inside the drop. Okay, if we like to solve the whole equation, how I can avoid this kind of happen, that the surfactant goes inside the interface. Okay, so then we propose an embedded bulk concentration equation. Rather than solving the moving irregular domain, we solve embedding the equation to the whole domain. Okay, that will make our life easy, because we only have to solve it in PD in irregular domain, irregular Cartesian domain. Then we use finite difference to solve this equation. To do that, we introduce an indicator function, which is proposed by Treverson in 1992 for ground tracking. And basically, this indicator function is just a Heaviside function, nothing special. Then put that equation, modify the bulk concentration equation. And rather than, this is the C equation, the gamma equation is the same. Okay, the C equation, we modify the C equation to be this way. So rather than numerical flux across the boundary, we write the equation as a singular source in the equation. Okay, this is the equation. So basically, we can, when h equal to 1, we recover to original equation, h equal to 0, which is inside. I make sure that the inside there's no surfactant. Okay, and then CS can be calculated easily. Okay, so the most important is this rate of change of surfactant. Okay, this equation, then you can see the rate of change of the surfactant still as the original one. So basically, in here we still have the total surfactant mass, which is conserved. Right? Okay, so let me show you the numerical results, numerical scheme. So basically, when U is given, so you know velocity, you move the interface. Okay, you move the interface, then you compute the indicator function h. Okay, which is because h is like a Heaviside function, right? So gradient h is like a delta function, right? Then you solve this Laplacian h of this equation. Basically, we solve that in discrete. Just discretize this whole thing, okay? And there's some accurate issues that can be found in our previous papers. Okay, so I skip that. Then we update, once we have the indicator function, then we update the surface concentration. This is our surfactant equation. then we multiply this structure partial x partial s. This is structure rate, okay? And this structure rate, this is the surface Laplacian. When you multiply the partial x partial s term, then become this one, and this is still our source term, all right? So then it's important to recognize that this term, okay, become this one, which is the rate of change of structure factor, okay, which is equal to what? This is not, not, it's familiar to us because if you study the fluid mechanics book, okay, this is Jacobian. The derivative of Jacobian equal to divergent U times Jacobian. Okay, so basically it's the same idea. So when fluid is incompressible, meaning divergent U equal to 0. When fluid is inextensible, okay, which is the reciprocal case, then the surface divergent U equal to 0, meaning that the local stretch, you cannot stretch your interface. Right. So then we solve that equation. Okay. Basically use a Kronecker scheme. Okay, so I'm going to skip that because it's a little bit detailed, and then we compute the bulk surfactant equation. Okay, and we also discretize it in Kronecker scheme, right? So okay. And then the source term should be written is just discretize the source term, okay? And the delta function was replaced by this smoothing delta function, okay? And then we can have this total surfactant. The original, we need this mathematically. We need this total surfactant mass is conserved, okay? Then for the discrete conservation property, we can prove that the previous scheme satisfies this total surfactant mass. Okay, this is the total surfactant mass in the bulk fluid. This is total surfactant mass along the interface. This is 2 at the n plus 1 times that equal to n times that for the previous scheme. Okay, so basically you just need to add up those, calculate those sum, okay, and then use the boundary condition, and that's it. Okay. So, and then we can put our solvable surfactant. This is a method that what I show you in the beginning, that the droplet collision, we use this scheme to simulate that problem, right? Okay, so skip that. This is just a numerical scheme, a detail. So solving the Navier-Stokes, then we move the interface, then we solve the surface and bulk concentration equation. That's the basic idea. So the bulk diffusion. So this is a numerical test. Okay. Okay. So what you see here, this is diffusion. So what you see here, this is the case. This is 2D case. We just make some cross section to make sure this drop inside is 0, right? So this is only diffusion. So you can see initial here. So you can see the diffusion effect, right? And then I think I will skip that. And you see that the arrow is the machine arrow. This is the upper plot is for the relative error of total mass. Okay, the lower plot is for the leaking error relative inside the interface, because we are solving the equation in the whole interface. Whole domain. So in the inside, supposed to be 0, but because we are solving that in the whole equation, so there's some concentration inside the interface. But I have to control that. This is our total relative error is 10 to the minus 5, meaning that the percentage is like 0.002%. Okay, so it's quite tiny. Okay, then we try different convection diffusion equation for this one. I'm going to skip that. I'll show you the one which is interesting. This is called a drop under shear flow. Okay. So the drop under shear flow will be that you put a drop, okay, initially there's no bulk concentration, but they have a surface concentration imposed, okay, along the interface. Then you have a different parameters, right? So this is basically this is a benchmark test. Everyone doing this kind in our society community. They will do this kind of test to see whether your code, your numerical scheme, your method is right or not. Okay, so basically it's benchmark test. Okay, so here the red one is the solvable case. All right, the blue one is insoluble case. So because the surfactant, it is the solvable case that the surfactant will dissolve from interface to the bulk fluid. Okay, so that means the surfactant along the for soluble case, the surfactant concentration is less. Okay, that means that you have a stronger surface tension. Right, stronger surface tension. You see, when your shear stress is not strong enough, the surface tension will bring your interface back to a little bit, so that you can tell that in this picture. So basically, this is the problem about the interfacial flow with the surfactant. Okay. So now, because I have around 5 minutes, all right. So I'm going to talk about another. Just let you see some pictures. Okay. Vascular dynamics in incompressible fluid. This is try to mimic the red blood cells. Okay. This is the red blood cells. Your red blood cell. It's important. The red blood cell try to carry the oxygen. The reason that I can stand here is because my red blood cell is working. All right. And carrying the oxygen into this red blood cell. But red blood cell can be deformed significantly, okay? Because some kind of vein is very tiny, so red blood cells still need to go inside, okay? So red blood cell can be deformed. This is our numerical simulation, okay? But look like doesn't mean we are right, okay? This vesicle is you have fluid inside and outside, okay, and then you have interface, okay. This interface is incompressible, meaning that, okay, this whole thing can deform, but this is resistant to area dilation, okay. That's inextensible, okay. I'll show you what that means. This is the mathematical formulation. This is the Navier-Stokes equation, okay? Again, this is defined in fluid domain omega. But along the surface, you have some constraint which is divergent U, surface divergent U equal to 0, okay? So that means you're solving PDE, but you're solving PDE with some surface, but surface have some constraint which is also PDE, and the surface is moving. Right? So the force can be written as this bending and sigma, because here is okay, but you enforce another constraint on sigma, on the interface. So you have to, some kind of introduce another function which is defined on sigma, right? To make sure that your equation, well, at least the number of unknowns equal to the number of the equation. So this is the bending force, which is related to the mean curvature and Gaussian curvature and the surface Laplace of Gaussian curvature. Okay, and this F sigma is called tension force, which is the sigma here, unlike previous problem, the sigma related to the surfactant concentration. Here, sigma is unknown. So basically, you have to solve PDE, which is there's some unknown function along interface, and then you have some constraint along the interface. Okay, so how to solve this problem? Okay, that's the issue. Okay, so sigma is unknown tension to be introduced to enforce this surface divergent U equal to 0, and the pressure and tension. So pressure is like a And this elicitation have the same role as a Lagrange multiplier. Okay, so pressure is the pressure in compressor flow. You can treat like a Lagrange multiplier to enforce divergence U equal to 0. Okay, and sigma here is the same role to enforce the surface insensibility. Okay, so they just Lagrange multiplier. Where we get the force? Okay, variation derivative. Okay, so different numerical issues and challenges. So first, you know the one you need to find the mean curvature, surface Laplacian mean curvature, and Gaussian curvature on moving surfaces. Okay. And also you have to put some constraint on that. Okay, so it's quite of a difficulty you have to encounter. All right, so can we skip that also? Here is I should play some movie. Okay, so right now, so for the vesicle, okay, you have some kind of a 10 trading. So let me play some movie. And 10 trading. Huh? Okay. So, all right. So 10 trading, you know 10, okay? 10 trading. Basically, you can think about this as a vesicle, okay? This is shear flow, okay? Shear flow applied to the vesicle. Vesicle, it's not like a drop. Okay, if you drop, they will deform further. But because this insensibility, so the shape doesn't change. But the shape doesn't change. There's some flow coming this way. So this guy, this is like a 10 trading. Okay, so this is called a 10 trading behavior. You can see in the experiment, right? And and another one is called tumbling. Okay, tumble. Okay, tumble like a solid particle. Tumble. And tumble is also seen in experiment. When you add the viscosity, this is sorry. Okay, so as long as the viscosity passes some critical contracts, then the behavior will change from 10 trading to tumbling. Okay. All right. So. Okay. So a few slides left. Okay. So basically, we compare with theory. So this is a case theory, Keller-Salak theory. This is joint work with Yongsam Kim, which is my academic brother in Korean Chongan University. And okay, so we solver have some kind of, we put some solid particle inside there, okay, to mimic the behavior. So this is 10 trading. When you solid small filling fraction is you have a small filling fraction, and then once you have a bigger filling fraction, then it's become tumbling, right? Okay, so this is last. Okay, so red blood cell, the healthy red blood cell is going to look like this, okay? But this is from simulation, okay? Not that big, okay? And then the last movie is the vesicle in gravity. Here. So when you can see this pier-like shape in experiment. When you put the droplet under gravity, you will look like this one. Okay, appear like a shape. And I think I will go to the last slide. Okay. Okay, so basically I think what I see here is you have to compute the surface quantity. Okay, in recent years I'm more interested on this to compute the surface quantity. For example, there are a lot of applications. Like I said in the previous slides, you will see that I need to construct a surface to compute the curvature, the mean curvature, the surface Laplacian of mean curvature, Gaussian curvature, and also there's some PD on this surface. Okay, so there are a lot of interesting things, and also a lot of applications, especially in computer graphic visualization and animations. Okay, and also personally, I'm more interested in fluid dynamics. Okay, because fluid is in everywhere and everybody on every day, and I think applied mathematicians play a major role in fluid dynamics community. And on the other hand, I will tell you that fluids are easy to drink rather than to understand, both mathematical and physically. Thank you for your attention.
Thank you for your talk. So, one question. Let me make a last remark. Applied mathematics plays major role in fluid dynamics. Means play major role in establishing the time sample. He is also the president of the Asia sector of science. So no more questions. So we have a small clip and
yeah, so couple of questions. So, and I'm saying this because we cannot do it. So, sure, okay, you can formulate this in R3, which is where these things live, but is your analysis actually in R3, or it's on the plane, the analysis?
Analysis, okay. For the vesicle problem, okay. Well, we in fact from my group, okay, we didn't do the analysis because there's a PD on the surface, and then there's some constraint, okay, on the moving surface,
Right.
okay. So
Yeah.
yeah, but I don't know. Okay, maybe
Right.
you can.
And just one last question. So again, I don't know how to do it.
Yeah.
This is for one droplet in a medium, right? Can you do, say, for example, soap bubbles, where you have a network of bubbles, and the surge factor can be actually between two bubbles?
Oh, yeah, that would be, we actually do some kind of phone simulation, but without surfactant. We assume the surface tension is fixed. Okay.
You don't put surfactant?
No, I don't put surfactant. Okay. Yeah. Okay, thank you very much for your talk. Okay, thank you.